A longbow with a 300 Newton draw weight at 50 centimeters of draw can be modeled as a perfect spring. If the mass of an arrow is 75 grams, at what speed can this longbow loose the arrow, assuming 100% efficiency? So I'm going to draw some pictures for this. I'm thinking like maybe here is the longbow with an arrow at full draw. And I'm going to describe this as the initial picture. Here's the arrow maybe. Maybe put little... Maybe I shouldn't have started with the fletches there, but whatever. There's some fletching on the arrow. And then the final picture is that the longbow is no longer stretched. And the arrow is moving here. Put a couple of fletches on it. Not necessarily a greatest looking arrow there. But it is moving with some velocity v. Okay. It says, though, that the longbow can be modeled as a perfect spring. So I'd like to look at maybe what I think is an equivalent system to this. I think an equivalent system to this would be to say, okay, here is a spring with a mass on it, and it's initially compressed. Oops. And we're going to have it on some frictionless surface, and that's going to correspond to my initial picture. And then my final picture with this spring is going to correspond to the spring has now uncompressed, and the mass is sliding off. Oops. Yeah, my picture might not be perfect here. Sliding off with a velocity v again. And it's a little more obvious here how, okay, we're talking about a spring that must have some spring constant k. There must be some amount of compression x that, in that sense, from an initial energy point of view, I think there has to be some 1/2 kx squared for the initial energy. For the final energy, I think it's 1/2 m v squared. And redrawing this picture kind of helped me to figure that out. Now, let's see. If I look at this in terms of like E initial equals E final, I've really got, let me just write that here. E initial is equal to E final. I have, therefore, 1/2 k x squared is equal to 1/2 m v squared. And since we're being asked for speed, I'm going to solve for v. Note one thing, though. I mean, part of my assumption here is that it says assuming 100% efficiency. So when I say E initial is equal to E final, I'm assuming 100% of this 1/2 kx squared got transformed into the 1/2 mv squared that represents the motion of the arrow or the block in the sort of equivalent system view of it. Anyways, we can solve for v, though, and I think we'll wind up getting that v, if I divide kind of both sides by m and then kind of square root both sides, I'll wind up with x multiplied by the square root of k over m. I did a little algebra in my head there because I know I'm going to want the space in a minute here. One of the issues, though, here is like if I look at now the numbers that are given to me, right? Like I think I can say that x, the amount of compression of the spring, corresponds to the amount of draw that was given there. So that's going to be equal to 50 centimeters, or maybe I'll just say it's equal to 0.5 meters. M is equal to 75 grams, which is 0.075 kilograms. But how do I find K, right? Well, recall that Hooke's law for a spring is F is equal to Kx. That means that K is equal to F divided by X, which is 300 newtons, because that's the amount of draw weight that I'm given. And really, keep in mind that draw weight for those of you who don't do archery, that's the amount of pull that the archer is exerting on the string here, which is really analogous to the amount of force that's applied to this spring in this case to keep it compressed. So anyways, modeling this again as that spring, 300 newtons divided by the amount of compression, which is again analogous to the amount of draw that, there's how much did the archer pull the string back. It's kind of the analogy, but divided by 0.5 meters gives me a 600 newtons per meter spring constant. And so now I think I'm ready to plug in some of these numbers, and I would get 0.5 meters times the square root of 600 newtons per meter divided by 0.075 kilograms. And I can put all of that into my calculator. And if you work out the units here, I mean, yeah, if you want to figure out this part, I think you'd have to work on it a little bit, but I think it winds up just being a 1/second squared, and then the square root would hit it and you get meter per second. But if you put just the numbers into the calculator, you wind up getting like 44.721359, etc. So in this case, I think I'm just going to round that off to 44.7 meters per second. And let's see if that answers the question. Looks like it did.